Before I continue with the duality theory, I just thought I'll check. I think from I wrote the, so this is in the last lecture when we were computing the solutions for the bounded variable problem. In the second table, in the second tableau, the top row, the 0 row, this entry, I was not sure if I had made it, written it correctly, but anyway, you can make this correction. If it is not there, it should be 3 by 5, and this of course we had computed finally. So I just thought I'll make sure of that. Then I had asked you to write down the dual, to write down the dual of the standard form of LPP, right. So the standard form would be minimize Z equal to C transpose X subject to Ax equal to B, x greater than or equal to 0. Okay, all constraints are equality constraints, and I will just write down the dual, and then you can verify whichever way you want. Okay, fine. Maybe I will demonstrate to you. See, the thing is that you can rewrite this as minimize Z equal to C transpose X subject to, remember, any equality constraint can always be written as two inequality constraints, and that would be Ax less than or equal to B and minus Ax greater than or equal to minus B. In other words, you would write this as Ax less than or equal to B, Ax greater than or equal to B. So, Ax greater than or equal to B, sorry, I will multiply by minus sign and get this, right, and then your x would be greater than or equal to 0. Okay, so I will give you that much hint, and you can now write down your, so your matrix A becomes, see, A minus A times x, and your right hand side is B minus B. So you can now write down the dual to this problem using the methods I have given you, and just see whether it's you get it in the right form. Okay. Now remember, for the dual problem that I wrote down for the primal in the general form, not the very general form, but I had some inequality constraints and some equality constraints. So I had this weak duality theorem, or the lemma, which is also known as the weak duality theorem. The weak duality theorem, which said that if x is feasible for P, that means a primal problem, and y is feasible for the dual problem, then C transpose x is greater than or equal to B transpose y. So this was our weak duality theorem, and this was, I could immediately, I had proved it to you last time. We derive it from the constraints and the definition of our dual problem. Now just see what you can all conclude from here. First, if x is a feasible solution to P, then the corresponding objective function value of C transpose x is an upper bound for the dual objective function. Right, because this inequality is valid for any y feasible for the dual and any x feasible for the primal. So here for any feasible dual solution y, the objective function value is bounded above by C transpose x. Right. So that means if I can find one feasible solution for the primal, then I know that my dual solution, dual problem is bounded, because remember the dual problem is a maximization problem, and here we are saying that the dual objective function value cannot exceed C transpose x, which is a finite value, right. So, there is no question of B transpose y going up to plus infinity. Okay. So, so this is it. So, that means, so this implies that if P is feasible, okay, that means I can find a feasible, and D is also feasible, then D is not unbounded. D is not, cannot be unbounded, cannot be unbounded, right. So, now you know for this for sure that if the P primal has a feasible solution, and if the dual also has a feasible solution, then only the question of unboundedness arises, right. Similarly, because you have this for any pair, so you see that you can immediately make the statement that if y is feasible for D, right, then the corresponding objective function value is a, let us see, is a lower bound, right, is a lower bound, is a lower bound for the primal objective function, for the primal objective function value, right. So, if I have any feasible solution for the dual problem, then provided, so then the C transpose x is greater than or equal to B transpose y. This is a finite quantity. So, therefore, again C transpose x, that means for the primal objective function value cannot go to minus infinity, or cannot be made as small as we wish, because it is bounded below by a finite number, right. So, the same statement can be made here, that is, now we will say that if D is feasible and P is also feasible, then P cannot be unbounded. So, just replace P by D and D by P, the same statement you can make here, that the problem is feasible, right. Now, thirdly is what can be the other conclusion? Fine, we will make some more conclusions from here, and that is, yeah, the third conclusion is, if, let us see, if I know for sure that this is unbounded, let us say the primal problem is unbounded, which means that I can make the objective function value as small as I want. So, it can go to minus infinity. What does that mean? This inequality, that means if the dual was feasible, then this value would be finite. So, what we would say, it would imply that something very small is greater than something positive, some finite number. That means minus infinity is bigger than some finite number, which is not possible. So, what would we conclude? If we know that the primal problem is unbounded, then we can conclude that the dual cannot be feasible, right. So, just with this inequality, this is all you can, so many things you can conclude. So, if P is unbounded, it would imply that D is infeasible, right. And similarly, the fourth statement, that if D is unbounded, it will imply that P is infeasible, because again if P were feasible, then this would be a finite value, but this can be made to go to plus infinity, since we are saying that D is unbounded. So, it is not possible, the inequality is not possible, but we derive this inequality from our definition of the dual from the primal, right. So, that takes care of your these things, and we will want to, we will further talk about, for example, there would be need to talk of a converse of 3 and a converse of 4, which I will come to a little later, but before that we want to get into the interpretation of the dual variables. So, even and before I do that, let me show you See, the idea here is that we started with a primal problem and then I defined the dual, okay, in a very natural way. From the optimality conditions for a primal problem, I could define a new problem which we call the dual problem. So, the question that needs to be asked now is, can I now from the dual, using the same process, can I define a new problem? No, the answer is no, because when I try to now look at this as a primal problem and define its dual, I will get back to P. So, this is the result that we want to prove. Theorem: dual of the dual is the primal. Okay. So, in other words, I will try to write down the dual of the dual using the rules that I used for defining the dual of the primal, and then I will show you that we get back to the same problem, and therefore, the process cannot go on indefinitely. I can only define the two distinct problems that can arise in this way, right. And this will further simplify the presentation of the theorems and so on. In fact, you can see that the 4 statements that I wrote would not be necessary if I had shown this. But anyway, I wanted to first look at that inequality and give you a feeling for it, and then we go on to showing that the dual of the dual is the primal. Okay. So, let us see, I need to quickly write down. So, what was my primal? The primal was minimize z equal to sigma Cj xj, j varying from 1 to n, subject to, let me just verify, the m was the first equality constraints or inequality constraints. How were we writing it? Okay, there I think I was using m bar, m for, okay, does not matter even if the notation is a little different, subject to. So, we were saying ai x greater than or equal to bi, I belonging to m, right, and then ai x, where ai's are the rows. So, ai x equal to bi, I belonging to m bar. Then we said that x j is greater than or equal to 0, j belonging to n, and x j unrestricted for j belonging to n bar. Then we wrote the dual as maximize psi equal to b I y I varying from 1 to m, subject to. So, this gave rise to your y I greater than or equal to 0. This gave rise to y I unrestricted, right, because equality constraints, and this gave you the conditions that summation, or okay, we are not writing summation here, we are writing in terms of rows and columns. So, this gave you the condition. See, this is a row here. So, the column, corresponding column we will write here. So, this will be A j transpose y. Okay. So, A j is a column. So, transpose becomes a row, row times y is a single number. So, this is less than or equal to C j for j belonging to n, right, and equality constraint. So, A j transpose y equal to C j for j belonging to n bar. So, this was our dual, right. Now, so in order to be able to write the dual of this, I have to first formulate this as a primal problem. So, what does that entail? That means, I have to convert the maximization to minimization, which can be done by multiplying by a minus sign the objective function. So, write the dual as a primal problem. And what would that be? So, I will write here minimize minus psi, which is equal to minus sigma b I y I varying from 1 to m. So, the b I has been replaced by minus b I, right, and this of course same conditions, yeah, except that, yeah, I should have said here I belonging to M and here I belonging to M bar. Okay. So, those remain the same. So, let me write this first. Now, here remember your constraints here are greater. So, I will multiply this by minus sign, and so this will give me minus A j transpose y greater than or equal to minus C j, and equality constraint to maintain uniformity I will write this as minus A j transpose y is minus C j, right, and then y I greater than or equal to 0, I belonging to M, and y I unrestricted for I belonging to M bar. So, now this problem is exactly in the same form, of course, the different dimension, but that does not matter. I know the rules for writing down the dual of the primal when the problem is formulated in this way. So, I now write down the dual. Okay. So, what would be the dual? Yeah, and please remember, see here this was a row A I, right. Now, in this case, so what is my corresponding matrix here? This A j is a column, I take the transpose, so that becomes the row. So, that means this is actually the row of the transpose. If I take the matrix A, see if I write the matrix A as A1 AM, right, then what would be, and so then A transpose would be A1 transpose, A2 transpose. See, these rows will become the columns, right, and here now I need the row because AIX greater than or equal to BI. Okay. So, you will take the so in other words, okay. So, what I am saying is that for this problem your matrix is A transpose actually. So, the A transpose matrix, the columns become, so if you write this, you can also write as A1 AN, right. So, when you take the transpose, it will become A1 transpose, A2 transpose, AN transpose, okay, and that is what is happening. So, here essentially the matrix is minus of A transpose, this is the thing, right. So, when you, and you need to, so that these are the rows now. So, when you take the transpose, you get the this kind of rows, because this is the transpose of the column. So, when I take the transpose again, I will get the row in the row form, right. Okay. So, the dual would be maximize psi, or okay, let me write some other thing here, z bar equal to, so the right hand side the b's came into your objective function here. So, this will be minimize maximize minus Cj, and let me write Zj, right, j being from 1 to n, fine. Okay. Then for this, remember, so this was for all j belonging to n, for all j belonging to n bar. So, correspondingly, if you just follow this rule, I am doing that only, then it will say that Zj is greater than or equal to 0 for j belonging to n, Zj is unrestricted for j belonging to n bar. Okay. Yes, and then corresponding to this thing here, what is your, or okay, corresponding to y I greater than or equal to 0, what is it that you have? Yes, from here greater than or equal to 0, you had this thing here, right. It is just that your matrix is changed here. So, this will be minus A I z, and then we will have, what is it? Yes, see, I am writing the dual. So, my dual is right now in this form. Okay. So, for non negativity here I have this less than or equal to 0. Okay. So, this will be no, okay. See here, this is less than or equal to Cj. So, the corresponding Aj is, this is less than or equal to minus Bi, I belonging to M, right, because you have yeah, you have here yi non-negative or I in M. So, the corresponding thing here would be this constraint, right. For non-negativity there, I had this constraint. Remember that came from the optimality criteria. So, I belonging to M. So, this I have this, and for and minus A I Z equal to minus B I belonging to M bar. So, then I can rewrite these two as A I Z greater than or equal to B I belonging to M, and A I Z equal to B I belonging to M bar. So, if you look at this problem, and so here this is maximization of this. So, I take the minus side outside. This objective function can be written as minimize, right. You can write Z here. I can replace minus Z bar by Z, which is Cj Zj dividing 1 to n. So, it's just that the variable instead of the x variable, I am writing the Z variable, does not matter, but your primal problem, this together with this is the same. So, if I try to write the dual of the dual, I get back the primal problem. Okay. And so, now that means whatever results I have said so far, where I said for the pair PD is also valid for DP. That means, I can replace P by D and D by P. So, now nice symmetric relationship, and it simplifies lot of things. Okay. Now, with this I will try to, once we have this established, now I want to give you a little more feeling for the dual problem in terms of the economic interpretation of the dual problem, the dual variables. And so, I need to define, so I need to define the diet problem. So, the dual of the dual is the primal. Once we have this, so let us consider the diet problem, a housewife's diet problem. Idea is very simple, and the problem may look a little oversimplified, but I think it brings out the concepts of linear programming and the dual problem. So, just let us look at it. Suppose, so a housewife has to choose from n different foods, from foods 1 to n. So, n different foods are there. She has to choose different foods from here in different quantities to come up with a diet. Now, what are the features of, so actually she would like to have an adequate diet. Okay. So, for an adequate diet, which sort of gives you the required nutritions. So, for an adequate diet, 1, 2 to m different nutrients are required, and B1 to B2 BM are the minimum requirements. For the respective nutrients. Okay. That means, for the first nutrition, which may be protein, then you are saying that at least B1 amount must be there. Then carbohydrates, second nutrient is second carbohydrates, and you must have at least B2 units, whatever your unit of measure, gram or whatever. So, this you must have this, and so on. So, of course, one can say that maybe if fat is also a nutrient, then you should not actually have a lower bound for the fat, but you should have an upper bound. But anyway, then you can multiply by minus sign or whatever it is. I am just taking, as I said, a simple version of the problem. So, you may have constraints of the kind greater than also, because if you have fat or sugar, then you do not want to have lot of these things in the diet. There must be an upper bound. Anyway, so B1, B2, Bm are the minimum requirements for the respective nutrients. Now, the thing is that the different foods. So, for example, Aij will tell you the amount of ith nutrient present in jth food. Okay, you have this, and then you have Cj as the cost of a unit of jth food. Okay. So, with this data, what is she wanting to do? See, first of all, say you look at the constraint a1 1 x1 plus a1 2 x2 and so on plus a1 n xn. So, my decision variables, okay, x1 to xn are the decision variables. Are the decision variables. That means, x1 will tell me the amount of first food that I am going to include in the diet, x2 will be the amount of second food I have in the diet, and so on. So, with these decision variables, if I x1, x2, xn, you see this will tell me, remember I am assuming linearity and so on and additivity, axioms of linearity. So, then this tells me the first nutrient which is present in the first food. So, then this will be the total amount of first nutrient that my first food gives me. Then this will be the amount of first nutrient that the second food gives me, right, when I take x2 amount of it. So, this total is the, if my diet is made up of x1, x2, xn, then this will give me the total amount of first nutrient which is present in my food, and this must be greater than or equal to P1. So, similarly, you can have A21 x1 plus A22 x2, the second nutrient A2n xn greater than or equal to P2, right. And finally, you have AM1 x1 so on plus AMN xn greater than or equal to PM. So, these are your constraints which make sure that the diet that you finally choose or the housewife chooses is adequate. It meets the nutrition requirements. Okay. And of course, this is very natural, because either you will choose a food or you will not choose it. So, there is no question of negative amount of food being chosen. So, all variables must be non-negative, right, and she wants to, obviously a housewife has this problem of wanting to choose a diet which is economical also. It is adequate, but economical, right. So, minimize z equal to C1 x1 plus Cn xn. So, this is one formulation of the diet problem, the housewife's diet problem, and we can write it as in a short, in a matrix notation we can write this, and this is known as, so minimize z equal to C transpose x subject to A x greater than or equal to B x greater than or equal to 0, and this form is known as the canonical form. Canonical form of an LPP. Okay. So, minimizing the cost subject to the conditions that your diet is adequate, and this is it. So, this is a housewife's problem. Now, let us write down the dual to this, and remember here in this case the constraints are all greater, there is no equality constraint, and then so that means your m bar is missing and n bar is missing. So, write down the dual of the diet problem So, this would be maximize psi equal to B transpose y subject to, so simply take the transpose A transpose y, this is all non-negative. So, this will become or equal to C, right. Remember, because you do not have the m bar and n bar inequality constraints. So, you have y greater than or equal to 0. Actually, the canonical form is very easy to remember the dual, because for minimization the constraints have to be greater than or equal to kind. Non-negativity if you have, then this would imply that all your dual variables are non-negative, and this would imply that the constraints are less than or equal to kind. And if you can remember very well that see, for this minimization problem the optimality criteria would be of the kind Cj minus Zj is non-negative. So, you can remember. So, there are many ways in which you can remember how to write down the dual, and everybody can have one's own formula the way you interpret the. So, this is your dual of the diet problem. Okay. Now, there is an interesting side to it. Suppose there is a manufacturer who wants to manufacture different pills, pills for the different nutrients. So, a pill maker or a pill manufacturer, because and then he wants to suggest to the housewife, it is hypothetical, he wants to suggest to the housewife that instead of cooking up with a diet, I will provide you with pills for different nutrients, so that they together will give you an adequate diet. Okay. But then how can the pill manufacturer attract the housewife? In what way? So, let us say and just see, the dual problem is the maximization problem. So, the manufacturer prices the ith nutrient pill as yi units. Okay, that means yi rupees, you can say. So, he will price, suppose he wants to, now he has to decide what should be the price for the ith nutrient, right, and then yes. So, in other words, yeah, look at the first constraint here now, look at the first constraint. So, this is A transpose. So, remember your A is A11, A12, A1n. So, when you write A transpose, the first row of A transpose is the first column here, right. So, what will it be? So, the first dual constraint is, and let us interpret it, is A11 y1 plus A12 y2, and this is A21, right, and then AM1 ym less than or equal to C1. But you look at this now, the price of 1 unit of the ith nutrient is yi rupees, and A11 amount of first nutrient is present in the first food. So, A11 into y1 will be the value of the first nutrient in terms of the manufacturer, because he is pricing the ith nutrient as yi rupees. So, this is the total worth of the ith nutrient to the manufacturer. Then A21 y2 is coming from the second food. This is A21 y2, yeah. So, this is the second nutrient, the first index refers to the nutrient. So, A21 y2. So, that means for the first food the nutrient present in the second nutrient present in the first food is A21 per unit of the first food, the second nutrient. So, this is the total worth. So, this, the left hand side tells you the worth of the first food in terms of its nutrients, corresponding to the prices that the manufacturer is putting to these different nutrients. So, for the manufacturer, these are the values or the prices of the different nutrients, and A11, A21, AM1 are the different nutrients present in the first food. So, the total worth of the first food is this much, and obviously this cannot exceed C1, the price of the first food in the market, because if it exceeds C1, then why would the housewife be interested in going for the pills rather than the food? Okay, this is the kind of argument that you are making, just to help you to look at the other side of the linear programming problem. And so, this gives you C1, and similarly the other constraints. So, the second constraint will tell you that the worth of the second food in terms of its of the nutrients it contains, and therefore the value that is being accorded to these different nutrients by somebody else, by the manufacturer. So, the total worth of the second food should be less than or equal to C2, and this will be your second constraint. So, therefore, the dual constraints give you a nice way of looking at the constraints here, and it says that you are comparing the actual price of the food in the market to the worth of the food in terms of the nutrients it contains. It can be some other scenario, and therefore, it can be some other interpretation, but this is the kind of thing one will do, right. And then of course, the manufacturer also has to know as to what would be the prices for these different nutrients, so that his proposal to the housewife becomes attractive. So, but he would want to maximize his pricing. He would want to maximize, because he wants to maximize his gain subject to this constraint, because the moment he violates this, his proposal is not attractive. Okay. So, therefore, this is the dual problem, and so yi, in other words, the dual variables here are in a sense, you have this primal problem, you have the right hand side quantities. So, the dual problem, the dual variables are the in a way prices, or the for the other person, what would be the worth of these items, of these nutrients to the other person who wants to come up with an alternative way of making up this diet. That means in terms of pills, right. So, this is one interpretation of the this thing, and yes, and now you can look at the weak duality theorem also, which says that the C transpose X, the cost of the, so saying that the cost of the adequate diet should be always be more than the worth of the food to the manufacturer in terms of the pills, right. So, C transpose X is always greater than or equal to B transpose Y, and we will come back to the interpretations of the dual variables some more at optimality. What does it say? Now, let me come to the fundamental theorem of duality. We have already fundamental duality, and there are two ways of stating this. I will make the statement first. So, let me now give you the fundamental theorem of duality, which says that if x bar is optimal for P, then the dual problem D is feasible, then D also has maybe then D also has a then D also has an optimal solution y bar, and the two objective function values are equal. That is, C transpose x bar is B transpose y bar. So, let us prove this and then prove. So, if x is optimal, there is a basis B. So, prove since x bar is an optimal solution for P, there exists a basis B, right, such that, and this we have shown while I was defining the dual problem, such that y bar equal to CB B inverse. I think I used the y bar transpose CB B inverse is a dual feasible solution. the way we define the dual problem, I showed you that if B is the optimal basis, then the optimality criteria will be satisfied, and that means that y bar given by CB B inverse is dual feasible. So, if you just go back to the definition of the dual, you will recall this, right. Okay. So, this is dual feasible solution, and by definition, and C transpose x bar, which is nothing but CB B inverse B, because your basic feasible solution CB B inverse B, CB is the coefficient part, and then this is this, and this is equal to B inverse, right, B transpose CB B inverse. So, you can write the transpose and right same thing, because it is a single number. So, I take the transpose. So, so therefore, the two objective function values are equals. Therefore, I have shown you that is then D also has an optimal solution, and the two objective function values are equal. So, the proof is simple, because the way I constructed the dual, there is nothing much to do, but the implications are many, and we will show you. Now, of course, one can also state the fundamental theorem as saying that yeah, I hope there is no confusion. See, sometimes I may not write the transpose and so on, but it is all evident from the context, whatever, fine. So, another alternate statement would be what? Alternate statement of the theorem would be if x bar is feasible for P and y bar is feasible for D, then x bar is optimal for P. No, sorry. Yeah, one more condition is needed. I cannot say it like this. And so, if x bar is feasible for P and y bar is feasible for D, and C transpose x bar is B transpose y, then x bar is optimal for P and y bar is optimal for T. Okay. Now, again there is not much difference, because remember, if x bar is feasible for P and y bar is feasible from your weak duality theorem, what did we say? That if x is feasible and D is also feasible, then D cannot be unbounded. And similarly, if D is feasible and P is feasible, then P cannot be unbounded. So, once we know that the problem, both the problems are not unbounded, because both have a feasible solution. So, therefore, both will have finite optimal solution, and this, because you are given this, that C transpose x bar is B transpose y bar. So, you should be able to show by exactly following this proof, because since now, so therefore, now you have come here. So, if x is optimal for D, then D also has an optimal solution y bar, and the two objective function values are equal. So, now we will say that see the statement that if x is feasible and D is feasible, then x has an optimal solution, because x cannot the P cannot be bounded unbounded, and therefore, the rest of the proof follows. Okay. I would like you to just sit down and write the proof for this using that, because you just have to bring it from here. You conclude that P has a finite optimal solution, and because the two objective function values are equal, you will be able to show that y bar is optimal for. Okay. Yes, here maybe you can say that the proof is not complete, because I have shown you that the two objective function values are equal, right. I have shown you that this is B transpose y bar, but then why is y bar optimal for D? So, maybe I can complete the proof here, Yeah. So, we come back here and we say that I have shown you that there exists a feasible y bar for the dual problem such that the objective function values are equal, right. Now, suppose or okay, I do not have to suppose. Now, let y be any dual feasible solution, right. Let y be any other dual feasible solution, then x bar y is a primal dual pair of feasible solutions, and from the weak duality theorem, from the weak duality theorem, C transpose x bar is greater than or equal to B transpose y, because x bar is feasible for the primal, y is feasible for the dual. So, C transpose x bar is greater than or equal to B transpose y, but B transpose y bar is equal to C transpose x bar, and therefore, this is greater than B transpose y, where y is any dual feasible solution. So, therefore, this implies that B transpose y bar is greater than or equal to B transpose y for any feasible y, for any feasible y. So, this implies that y bar is optimal for D. Okay. So, I should have completed the proof there, right. Okay. So, this shows that I can actually have this is called a constructive proof. Given a optimal solution for the primal, I can actually construct an optimal solution for the dual. And so, that alternate statement you can also do the same thing, because you have this equality, and this will only happen when y bar is equal to CB inverse for B an optimal basis for the primal. Okay. So, this is this now, and you can immediately see that from the weak duality theorem I had the statement 3, right, from the weak duality theorem. Statement 3 was, what was your statement 3? Statement 3 was that if the primal is unbounded, it implies dual is infeasible. So, let me just look at this one, and then you can similarly write the converse of statement 4. So, P is unbounded implies D is infeasible. What would be the converse? So, converse would be, if D is infeasible, does it imply question mark, does it imply P is unbounded? So, this will be the converse. Now, you cannot the converse, you can, because what actually the converse would be that if D is infeasible, the primal can be unbounded or infeasible. Okay. So, because we said that the dual of the dual is the primal. So, and this part we have already said that if P is unbounded, D is infeasible, right. So, you can replace P by D and D by P. So, you say that if D is infeasible, D is unbounded, P is infeasible. So, right. So, here D is infeasible, you want to conclude whether P will always be unbounded, which is not true, because I can now take a quickly example here to show you that both can be infeasible at the same time. Okay. So, let us take this example, minimize z equal to x 1 plus x 2 subject to x 1 minus x 2 less than or equal to minus 1 and minus x 1 plus x 2 less than or equal to minus 1, x 1 x 2 greater than or equal to 0. You can immediately see that the problem is obviously, because x 1 minus x 2 less than minus 1 and minus of that is also less than minus 1. So, you can draw the thing, if you put this equal to 0, you have this thing here, then you have this here. So, the feasible region is this side, right, because 0 lies on the other side. Similarly, here when you put this equal to 0, you have this parallel line, right, and then this is minus 1. So, you have this, and this thing is this. So, problem is infeasible, right. This is infeasible. Quickly write the dual. Now, writing the dual, and of course, you can see this is minimization. You can either make it greater and then add slack, or you can just add slack variables and get the standard form and then write the dual, but treat this as an exercise and try to write the dual. This would be the dual. So, here y 1 y 2 are less than or equal to 0, because see here the constraints are not greater kind anyway. So, this is the dual, and when you plot it here, it turns out that this is the feasible region, and this will be unbounded, because y 1 y 2 are less than or equal to 0, and if you look at these two constraints, then they are represented by these two parallel lines, and then this is the region. So, in this case the dual is unbounded. So, primal infeasibility can imply dual unboundedness. This is one case I wanted to look at, and then the second situation is, if you take this LPP, okay, minimize z equal to x 1 subject to x 1 plus x 2 greater than or equal to 1, and minus, and the same constraint again greater than or equal to 1, and x 1 x 2 are unrestricted. So, in this case you see obviously it is infeasible, because the same quantity and the minus of that is greater than 1, not possible. So, and if you plot it, you see that one constraint represents this side and the other one this. So, the primal is infeasible, because x 1 x 2 are unconstrained. So, the whole it spreads on both sides. Now, again here you can write the dual. This is in the canonical form, and because the variables are unrestricted, therefore, the constraints would be equality kind, and you can immediately see that y 1 minus y 2 equal to 1 and y 1 minus y 2 equal to 0. So, this is infeasible. The problem cannot be. So, therefore, in this case I have shown you, given you an example, that if the dual or whichever problem you look at is infeasible, then the other will also be infeasible, can be infeasible. And here the unboundedness comes because the dual problem is feasible, the primal is infeasible, the dual is feasible, and therefore, it will be unbounded. So, both cases are possible. Therefore, the converse statement would be that if D is infeasible, then P is unbounded if P is feasible, right. So, we will write that P is unbounded if P is feasible, right. Otherwise, P is infeasible. Okay. The board has become a little is infeasible. Okay. This is the thing. So, and since we have already said that the dual of the dual is the primal, so you can interchange the statement P and D. So, what essentially we are saying, or we are establishing through examples, is that if one of the problems is infeasible, the other problem would either be infeasible, and if it is feasible, it will be unbounded. So, this is the proper converse of the statement, of the statement 3, and so through examples I just thought I will give you an idea. And now, I can quickly give you this chart for the fundamental theorem, which we will talk about in the next lecture also. So, you have P, you have D, then you have optimal solution, then you have infeasibility, and you have unboundedness, and here you have optimality, infeasibility, and then unboundedness. So, your chart will look like this. Okay. And now, when we have said that when both are optimal, when one is optimal, the other is also optimal from your fundamental theorem of duality, then if this is optimal, this is not possible. The dual problem cannot be infeasible or unbounded, right. Similarly, if P is infeasible, if this is infeasible, then this is not possible. Remember, we just now said that if P is infeasible, then the dual cannot have an optimal solution. It can be infeasible or unbounded, because I gave you an example that if one is infeasible, the other can be infeasible or it can be unbounded, right. Now, when this is unbounded, the dual cannot have a finite optimal solution, right, because it will imply that P also has a finite optimal solution. Unboundedness, this is true, right, and this is not true. Okay. So, the chart is complete, and now one can use these results in many ways. We will show you, and in fact, this will give rise to the fundamental theorem of duality, also gives rise to the complementary slackness conditions, which we will discuss next time, and also alternate ways of solving a linear programming problem.